Thanks for tuning into this virtual presentation. I'll be discussing formal controller synthesis for frequency regulation utilizing electric vehicles. It's based on the paper written by myself, Ben Wooding, Vahid, Vahidinisab, and Sadegh, Soudjani. Plug-in electric vehicles are important for future demand-side response. There's two main reasons, the first being gas and diesel vehicles are slowly being phased out, and secondly, the EVs can respond quickly to any power disruption events. Primary frequency response is the most useful service because the EVs respond quickly to the loss, and also there's minimal impacts on the vehicle battery when it's used in this scheme. We consider both unidirectional and bidirectional charging strategies of the EVs. The bidirectional charging includes signalling an EV to discharge energy from its battery back into the grid. Unidirectional charging is only able to stop or start. We consider 25,000 EVs in aggregation in this paper. Formal synthesis is the designing of a controller for a system that's guaranteed to satisfy a desired specification. Common specifications would include reachability and safety specifications, and the specification is written in a temporal logic. In this paper we use linear temporal logic. Since the state space of a system is continuous, we use abstraction techniques. We're able to represent partitions of the state space as symbolic states in an abstract state space. So a large number of states in the original system can be replaced by a single state in the abstract system. The mathematical properties of the abstract system are then used to ensure satisfaction for the original system. The abstract system and the original system are equivalent. So getting a controller for the abstract system means you can use that controller again on the original system with the same guarantees. The formal process will go into more detail in the next few slides. But firstly, we need to create a formal specification that we want to satisfy for our system. Secondly, we compute the abstraction of the system and get a symbolic model. Thirdly, we design a symbolic controller using that symbolic model. And fourthly, we apply the symbolic controller we've designed to our original system, having those guarantees. So we compute both the abstraction and design the symbolic controller using the SCOTS software tool. Our paper is designed as a proof of concept, so we created a simple GB model with dynamics, and we take a loss of 2,000 megawatts, which is loosely based on the power loss event of the 9th of August 2019. As you can see in the figure below, we've demonstrated a simulation of the baseline controller that we'll use for comparison. You can see that when there's no electric vehicle participation, the frequency falls below a containment zone of 49.2 Hz. This is something specified in the grid code that should never happen. So our specification is based on the grid code of the GB national grid. The first requirement is that mentioned before, the frequency should never drop below the containment zone of 49.2 Hz. When this occurs, low frequency demand disconnection occurs and lots of load shedding would happen. The second requirement is that if the frequency leaves the safe interval, we call it I1, then it should return within 60 seconds. Also, to demonstrate the strength of our method, we've added an additional constraint that when the frequency returns to I1, it must then reach a second smaller interval, I2. We have written this in linear temporal logic below at the bottom of the screen. The first section represents the first requirement, then the second section represents the second requirement, and the third section represents the third requirement. To convert to a symbolic model, we use the abstraction. So we have our system dynamics written as a partial differential equation, and we take that and we convert it to the symbolic model. The symbolic model consists of states, x, inputs u, and a transition relation f, which is based on the states and the inputs. So on the right-hand side, you can see a diagram. So for example, state x2 transitions to state x3 using input u2. So the arrow represents the transition and the circle represents the state. The inputs are written on each line. So this abstraction is done in the SCOTS tool. We pass in the system dynamics and the formal specification, and then we are returned a symbolic controller. Using the SCOTS tool, we then attempt to synthesize the controller. So transitions are removed from the transition relation if they do not lead to the satisfaction of the specification. So we have the symbolic model diagram again. You can see between x4 and x5, there is a transition using the input u4. This is removed in the symbolic controller which must mean that using that transition between states, we would not satisfy our specification. Scots also has a beneficial use in that the controller is only returned if we are able to guarantee satisfying the specification. Otherwise, it will return no controller. So the existence of the controller is a satisfaction guarantee in itself. The controller takes the form of a lookup table, and it returns the lowest input value which satisfies the specification for the given state. For our system, we treat the states to be the current frequencies or the frequency points, and we treat the inputs as the percentage participation of the EVs in the control. So we would pass in our current frequency to the controller. The controller would use the lookup table, and it would find a value which is then going to be used by us as an input as a percentage participation in our system for the next state transition. Finally, we have our simulation results. So you can see here for both bidirectional charging and unidirectional charging that the green state I2, the controller is able to direct the frequency into that. So we have the black region is I1, the green region is I2, and we designed the controller so that we designed the simulation so that while we were inside the black region to start with, I1, there was no control. When we leave I1, controller 1 takes over and returns us inside I1. And then after we've returned inside I1, controller 2 takes over and tries to take us into the smaller region I2. This is done for the symbolic controller, but the baseline controller is not able to do this transition. So you can see the symbolic controller returns the frequency to a better steady state value than the baseline controller did, and that this behavior is guaranteed as we discussed in the previous slides. However, this is at the cost of larger EV participation. Finally, our paper proposed a new approach for integrating the EVs for frequency response using the formal synthesis techniques. We did this by encoding a specification in a temporal logic rather than expressing it in natural language. Then we also enhanced our frequency response using a more robust controller design which has guarantees of returning to the safe interval. We then finally provided those simulation results which showed the correctness of our design, even with the more stringent controller. For future work, we intend to consider more complex models of the power system, such as the IEEE 39-bus test system and stochastic elements within the model. Thank you very much for listening.